Okay, so welcome to the course today. We are going to continue our investigations of the fundamental matrix and the essential matrix. And so far what we did, we described what is the fundamental matrix and essential matrix, how can we derive that, and how can we express it as a product of rotation matrices, calibration matrices in terms of the fundamental matrix, and a screw symmetric matrix encoding the baseline. Today we would like to take the other way around and say how can we actually obtain the fundamental matrix and essential matrix if we do not know where our camera is, but we know something about corresponding points in images. So consider we have two images, like those two images of the same building taken under different conditions, potentially, as long as the geometry of the object doesn't change, that's not critical. And we want to know the relative orientation between those two images. So how can we actually do that, or how do we want to do that today? We want to look into estimating the baseline as well as the rotation parameters based on the knowledge of corresponding points. So if we know some corresponding points, like those points, which let's say I manually label them. So I manually say, okay, this point over here corresponds to this point over here. And then I say, okay, this point over here corresponds to this point over here. So I'm doing these correspondences manually. Maybe I have a smart algorithm which does this. This is great, I can do that. But we can also assume that they are given by a human. So we assume we have those correspondences. So we know that this pixel over here corresponds to this pixel over here in the other image. And what we now want to know is we want to compute the fundamental matrix and essential matrix with the goal of obtaining, for example, the rotation and the baseline information about the camera from which location these images have been taken. So that's kind of the focus of today, and we look into different techniques to do that. We will study today the so-called direct methods. That means I can directly compute a solution without an initial guess. This may not be the optimal solution to achieve that, but this can serve, for example, as an initial guess for a least squares solution. And this is a technique which provides you already a pretty good estimate of these for the essential matrix or the fundamental matrix. So we will start with the fundamental matrix, look into kind of the standard algorithm, which is so-called 8-point algorithm. Then we look into how can we do that? Can we do better? And just we'll very briefly sketch an idea how we can do that with a smaller number of corresponding points. Then we are going to look into the essential matrix, and then the question, how can I actually obtain the rotation matrix and the basis if I have an essential matrix. So that's kind of the rough schedule of today and kind of the three big blocks, whereas we will discuss different techniques in those blocks and how to do that. And there's also the further information, it's more in detail, so we will start with the so-called 8-point algorithm for the fundamental matrix, then see if we can do that even with a smaller number of points, so with 7 points. We look into the computation of the essential matrix using basically the same algorithm, slightly adapted, and then look into special cases. So if we have some background information about how the points have been selected, or if I know already, let's say, the rotation between the two cameras, but on the baseline, how I can do that more efficiently. And then we'll come to the 5-point algorithm. We won't discuss the 5-point algorithm in detail. This is today the standard approach for estimating the essential matrix given corresponding points. It only needs 5 corresponding points, but we will very, very briefly sketch the idea, and then finally look into the last block, how do we obtain the rotation parameters and the baseline, given we have an essential matrix. So that by the end of today, if you have images and corresponding points, you should be able to compute the relative orientation. Just knowing corresponding points, not knowing anything further about the camera. If you use the essential matrix, then your camera needs to be calibrated. For the fundamental matrix, it doesn't need to be calibrated. Okay? So that's kind of the topic of today, and we start with the first block, computing the fundamental matrix from corresponding points. First, quick reminder, how does the fundamental matrix look like? So we have this expression over here, so involving calibration parameters, rotation parameters, and the baseline. And the important thing is also the block we're going to exploit, again, is this coplanar constraint. That means if I have corresponding points, then multiplying it from the left and the right-hand side to this fundamental matrix must be 0 if this is if these 2 points are corresponding points. Okay, and that's what we're going to exploit. So far, we looked into two means for obtaining the fundamental matrix. We assume we know the calibration matrix, the rotation parameters, and the baseline. Then we can directly compute it, or we just know the projection matrices of the two cameras, and we also can directly compute that. That's what we have done so far. But the question is, how can we actually compute f if we only know corresponding points in the images and nothing else? So that's kind of the problem that we're addressing now. We can start with the problem formulation. Consider we have those corresponding points, so in the first image and in the second image, and we have n of those images. We want to compute this fundamental matrix over here. So this is kind of our target. I told you already that we are going to exploit the coplanarity constraint. Of course, this is kind of the key information that relates corresponding points and the fundamental matrix. Do you have any idea how we could start trying to estimate the fundamental matrix given that we had those corresponding points and we don't know anything else about our camera? So we have two images, labeled those corresponding points. Any idea what we could do to get a glimpse of from which location those images have been taken up to the scale?
Yeah. We can use it, what's it called?
Coplanarity constraint?
Coplanarity constraint.
Yes, this is what we're going to want to exploit, that's true. And that's how it looks like. Anything else? What can we do? So these x are kind of given. These are our corresponding points. We know the pixel locations. And f are our unknowns. So the elements of this matrix are our unknown that we want to estimate. First thing we can do, we can actually expand this expression just according to the definition. Say, okay, these are our known points, and these are our unknowns. So we know that we have 9 unknowns. So these guys are our unknowns. And what we now want to do is we want to build up a system of linear equations that has those 9 parameters as the unknowns. The goal is then to solve this system of linear equations and with the solution of this system obtain those 9 parameters. And we can put our 9 parameters in and we have our fundamental matrix. It's kind of the overall scope. Okay, so the first thing that I want to express here is that the functions that we have, given that these are known parameters, and I have a function which depends on those 9 parameters, on these individual fij's, that there's a linear dependency. So we have just a linear function of those elements. And this becomes clear if I actually compute this product of matrix and 2 vectors. So what is this expression over here? I compute this by multiplying x prime with f11 x double prime. This gives me a first block over here. Just in this case, just rearranged. I can do the second thing as well. I can say, okay, then plus this element multiplied with this element multiplied with this element. This element over here. And I can simply continue that and so on and so forth. So I can actually do that and get this equation which consists of multiple sums. And the key important thing is that in every of those elements over here, fij is a linear element. It linearly depends on these 2 known parameters that I have. So these are knowns, x are knowns, and f are the unknowns in this case. So I can actually slightly rewrite that and kind of can group all those guys together for all elements, put them into one vector over here, and can do the same thing for my vector of unknowns over here. Well, the only thing I've done now, I've rewritten this product of 2 vectors in a matrix, which was 3 by 3, into a product of 2 vectors in the size 9 by 1. Because we obtain 9 elements through these multiplications. And I can simply rewrite this in this form. And this kind of, again, emphasizes the fact that this is a function which is linear in f. So it's a linear function, linear dependency. So I can again then take this expression, say, okay, I'm going to rewrite this as a product of a vector A and a vector F. And this is exactly my vector A and my vector F. So if I compute the product of these two vectors, I have my equation which should be 0. This is clear up to this point what I've done. I've just rewritten the term, and the goal was, why have I rewritten this? In the original formulation, those 9 unknowns were sitting in my matrix over here, but I want to have a vector of unknowns. So just kind of rewrite this in this vector form. Okay. And so what I've done now is exactly the same thing we have done in the second lecture of the course with the Kronecker product. So what I've exactly written here is the Kronecker product of these two individual elements, these two vectors. So these are all combinations of the individual dimensions of these two vectors. And then vec of f, which is just a form which takes a matrix and puts it into vector form, just stacking the elements on top of each other. So if I have a matrix, let's call it A, and it's a 2 by 2 matrix which has the elements A, B, C, D, then what vec A does, simply turn that into a vector which says A, C, B, D. So just takes those elements and stacks the columns on top of each other. This kind of, I can actually do this rewriting in general for a general product of two vectors in a matrix, especially in this here. And we actually use this from time to time whenever we want to turn the elements of a matrix into a vector of unknowns. Okay, so we have that. Okay, we have that, and we did that now for. So we get this expression over here for each corresponding point. So every corresponding point generates me one of those coplanarity constraints. So it's still exactly the same coplanarity constraint that I had before, just slightly rewritten by rearranging those elements. None of the elements has been eliminated or anything like this. I've just rewritten those elements of the coplanarity constraint into this form that I have a vector multiplied with another vector, and this should be 0. This was done for one point, for one n. I have, however, capital N of those corresponding points. So I can actually repeat this process and do this process for every pair of corresponding points. So for the first pair, for the second pair, third pair, and so on and so forth. And if I get this, I can simply say, okay, from this expression for one corresponding point, I simply build a matrix A, which takes these individual vectors an here as their individual rows. The first row corresponds to the first pair of corresponding points. The second row corresponds to the second pair of corresponding points. And I now build up a matrix. And if I multiply this matrix with my vector f, this should be 0. So it's just a concatenation of the coplanarity constraint for all points. So just to summarize this, because it's actually not very difficult. The only thing we have done, we have taken our matrix, the matrix contained of unknowns. We turned that matrix into a vector just by stacking them on top of each other. And then I defined this new vector A, so that if I multiply A with this vector f, I obtain exactly the same elements I would obtain if I would multiply the vector matrix vector in terms of the coplanarity constraint. I do that for one corresponding point, or one pair of corresponding points in the left and right image. And then I repeat this as for the first step. And then I repeat this process for all the corresponding points that I have. And so I get a number, so if I have n corresponding points, I get n of those products. And I can simply rewrite this again by taking those vectors and put them into matrix form, and then multiply A with f equals 0. And this is my coplanarity constraint for all the corresponding points. So what I've done now, I've turned the coplanarity constraints of the individual pairs of corresponding points into one single equation where the unknowns are one vector, 9-dimensional, that contains the individual elements of the fundamental matrix. So the only thing I have to do now, if I want to compute my unknowns for my given matrix A, I need to solve this system of linear equations. And this is a 9-dimensional vector because I have 9 elements of my fundamental matrix. So how do I solve such a system of linear equations? How can I do that? This type of equation, ax equals b, or in this case af equals, no, ax equals 0, in this case af equals 0 because f are unknowns and not x, as is typically the case. Something which is called SVD, singular value decomposition, which you all should know, which I can actually use to compute, to solve this system of linear equations, which provides a solution to this system. And this solution f are those elements of the fundamental matrix. So if I solve this, if I obtain my vector f, then I can simply need to rearrange those elements again and have my fundamental matrix. So if you look to this equation, what it says is that basically f is a right singular vector of this matrix A, and this is the one which corresponds to the singular value that is 0. So this matrix A has one singular value which is 0, and f is the corresponding singular vector, so the right singular vector corresponding to this one. Okay, so the question is, how many points do I actually need in order to build up this system? We said f is a 9-dimensional vector. So how many corresponding points do I need? 9 would be the straightforward solution to that. I know, however, something about my fundamental matrix. And the easiest thing I know is that it's a homogeneous matrix. And the homogeneous matrix has only 8 degrees of freedom. So what I need is 8 corresponding points, because matrix A has the rank of at most 8. We have this rank deficiency we also discussed. We can actually do better because we know that f has 7 degrees of freedom. So in theory, 7 should be sufficient. But for this approach over here, we stick with 8 corresponding points. And we'll discuss then how we can use the 7 corresponding points afterwards. Okay, but if I have 8 corresponding points, that's fine, but I may have more corresponding points. And the more corresponding points I have, the better actually my estimate of the fundamental matrix should be, because there's always noise involved. The points are never perfectly determined, the locations of these corresponding points. So in reality, we have noisy measurements. We cannot locate with infinite precision the individual corresponding points in our images. So one of the things I can do is I simply take more than 8 points for computing my matrix A. The problem that I have, given that I have this small noise in there, that then my matrix A would not become a singular matrix. So would have full rank, or rank 9. Well, that's something I don't want, because I have this rank deficiency in my fundamental matrix. This was something which is core to the fundamental matrix. So what we see quite soon is that we actually need to fix this, or not fix this. What we're going to do in the first step is we say, okay, then let's take the right singular vector that corresponds to the smallest singular value. Because it's not 0 anymore if I have noisy measurements. Okay? Okay, so let's have a look how this works exactly. So I have matrix A. I compute my function SVD in MATLAB, or however I do that, and I obtain these 3 matrices. Okay, I can actually illustrate those matrices. So this is here I have n elements, 9 elements, and n is the number of corresponding points I have, so at least 8, but potentially more. Then I have this matrix U, which is an n by n matrix. I have this matrix D, which looks like this, and here I have the singular values on this element of the diagonal. and I have this 9 by 9 matrix here, V. So what are sitting in here are the individual singular values, and typically, depending on the function that you use, typically they are sorted, so largest one towards the smallest one down here. And if the last one is kind of the smallest one, in the perfect case 0, this element here of V transposed is the right singular vector that corresponds to this smallest last singular value of this matrix A. So if I have my matrix V, this V transpose V, this last column over here is my estimate of my vector F, which are the elements of the fundamental matrix. Okay. So let's start turning this into an algorithm. I want to write a MATLAB code which is able to do that. So the first thing we need to do if we want to write our MATLAB code is, okay, we have our function compute fundamental matrix from point pairs. And I have here x prime, x double prime. And the first thing that I do, I need to build up this matrix H. Matrix A, sorry, not H, A. And I can actually do that by saying every row in this matrix A is generated by the Kronecker product, where MATLAB gives you the function cron, of the individual vectors from our corresponding points. So just need to iterate over all corresponding points and then can compute this matrix A, which consists of the individual elements of x and x prime, kind of all combinations of them. Every row of A consists of this. Okay, then the next thing I need to do, I compute the SVD, so singular value decomposition of A, obtain my U, D, and my matrix V. And what I then do is I take the last column of this matrix V and kind of reshape it in a form that I turn this 9-dimensional vector into a 3 by 3 matrix. So this was kind of, so this element here is a singular vector, or right singular vector, corresponding to the smallest singular value. Okay, now I have my fundamental matrix F, and I'm happy. I think I'm happy. But in reality, I'm not happy. The problem why I'm most likely to be not satisfied with this, and this matrix F doesn't necessarily has rank 2. And the rank 2 is was one of the constraints of this fundamental matrix. So I said before, I think I said rank 8 a few slides back, which was obviously a mistake. I was talking about the degrees of freedom, where 8, but so we have a rank 2 matrix. Sorry for this. So the fundamental matrix has rank 2. This is one of the constraints that I have. This F is not guaranteed to have this property. So I want to fix F. I want to fix this estimate of F so that I get a new matrix which is as close as possible to this matrix F but has this rank 2 constraint. So our goal is enforce rank 2 but come up within my new F should be as close as possible to the F or the F hat that we computed so far, but should have this rank 2 constraint. Any idea how we can actually enforce this? How can we generate a new matrix which exactly fulfills this condition? As similar as possible, but rank 2. So to help you a little bit, this estimate of F that we have is likely to have singular values, and if it does not have rank 2, one of those singular values, all the singular values are unequal to 0. But we said we're just very close to our solution. So it's very likely that one of the singular values is very close to 0, but it's not 0, but close to 0. And the two others are likely to be larger. So what I can do is I can replace a matrix F hat by a new matrix F by setting this one singular value which is close to 0 to 0. right? So the idea is I have a matrix F which doesn't have rank 2. I want to turn it into a matrix which is as similar as possible as F, but has rank 2. What I can do is I can inspect the singular values, take the smallest one, and set the smallest one to 0. In order to do that, I can again exploit the singular value decomposition, because what the singular value decomposition does, it turns A into this product of 3 matrices, and the matrix in the middle, the matrix D, is exactly the matrix which has the singular values on its diagonal. I simply take the smallest one out and set the smallest one to 0. That's kind of the trick that I'm doing. Yes, please.
Wie nah an Null muss dieser Wert denn sein, dass ich das, sag mal, guten Gewissens machen kann?
Okay, so how close does this value has to be close to 0? So the question is, it should be close to 0 if you pick your corresponding points correct. So you will have an error in your corresponding points because you can't locate them perfectly. And this is the only source of error that we have in here. So if you have very wrong outliers in there, this value may be very large compared to those others. And so this could be an indicator that you selected your corresponding points in a suboptimal fashion. But typically you should have one value which is very close to 0. I mean, it also depends on how many points you have. The more points you have, the larger the errors that you have in this process, because you basically accumulate the error of all the individual corresponding points. So what we do is simply we take our matrix F hat, and of F hat we compute an SVD. So we compute the SVD of F hat with U, D, and V transposed, and then say, okay, let's simply take those elements and modify D by setting the smallest singular value to 0. So take the 2 largest ones and say, okay, I replace this by this U, V transpose, and D I replace by just taking the 2 largest singular values. And then obtain the matrix F, which is as close as possible to my matrix F hat that I estimated from solving my system of linear equations, but which has this rank 2 constraint. So I can go back to my 8-point algorithm until here. That's what we had before. I only replaced F by FA, A for approximation. And then add another singular value decomposition, now not using the matrix A, but FA. So I'm decomposing my matrix F, which is a 3 by 3 matrix, using this SVD. And then I'm generating my new matrix F, which uses exactly the matrix U from the singular value decomposition of the approximation of the fundamental matrix. Take the 2 singular values, set the third one to 0, and then multiply with V transposed. And so with this approach, what I obtained is enforcing this constraint that the fundamental matrix has rank 2. And this is the full 8-point algorithm, or let's say the very basic form of the 8-point algorithm, which I can use in order to compute the fundamental matrix given 2 images and at least 8 corresponding points in those images. The more the better. Okay? So any questions up to this point over here? Okay. So there are a few things I need to be careful with in this setting. The first one is, if I solve this system of linear equation, I need to check, or it's a good idea to check, if there's a well-conditioned problem. So you can use the condition number, which tells you if you vary your input parameters a little bit, how much do the output parameters vary. And the smaller this condition number, the better the system that you want to solve is. We are working with these homogeneous coordinates, so if you have an image, let's say 3,000 by 4,000 pixels, and let's say I center the 0 around here, taking this pixel here into account would give me this vector over here. You can see already from this vector that you have some values which are rather large and some values that are rather small, which typically leads to a high condition number and a badly conditioned or ill-conditioned problem that you have. So what we can do is we can actually generate a new coordinate system which takes those points over here and maps it into a different coordinate frame where all the values are roughly along the same scale. And this leads to a better conditioned system, and this is numerically more stable. And this is actually essential for getting a robust version of this algorithm to do that. This transformation over here into a new coordinate system is actually a very, very easy one. The only thing that I do is, so the center of the image is the center of my coordinate frame, and then I scale this so that the points lie between -1 and 1. So they're all centered around 0 and take values between -1 and 1. So it's a very simple, it's called a normalization of the point coordinates. It's a transform so that either the center of the image or the center of mass of all the corresponding points, because I'm not interested really in the image, but in the coordinates of the corresponding points. So that the center of mass of the corresponding points is at 0, 0, and that the elements lie between -1 and 1, the individual coordinates. And then I can apply exactly the same approach that I did before to compute my fundamental matrix or essential matrix. So what I need to do for this conditioning, so this E should be actually an F. It's a copy-paste mistake, but it holds for E as well, so we can leave that here. So in terms of normalization, so what I do, I transform my system, my coordinate system, so that it is 0-centered and the elements lie between -1 and 1. Then I compute my fundamental matrix or my essential matrix. But what I then need to do, I need to actually turn it back into the original system. So what I need to do that, if I have my essential matrix from the original points, say, okay, I transformed my points with my transformation T, turn that into X hat, and then I get this E hat or F hat over here. This is just the product of the essential matrix with a transform. So if I want to convert from the essential matrix that I estimated to the original essential matrix, I just have here T transposed T. So there's a very easy mapping between this transformation and the essential matrix that I computed, because I computed the essential matrix for this different coordinate system, and so I need to do the mapping back. Yeah.
So you talk about the essential matrix?
So yeah, so this is a mistake because I copied this. So later on we do the same with the essential matrix. I just copied that slide. So CE as F. I'm sorry.
I understood that, but I was not looking for the word. So the text should be determined fundamental matrix.
Yes. So because it's just so this matrix, this slide will appear later on when we talk about the essential matrix. I copied over and I seem to have forgotten to replace the E by an F and the essential matrix by a fundamental matrix. But the rest stays the same in here. Das gleiche, so this holds for the essential matrix as well as for the fundamental matrix, holds for both. Yeah. So sorry, I'm going to fix this slide. So this is one of the things, one of the normalizations that I need to do. There are, however, some situations where where I can't obtain a solution. One of the things where we have the singularity is if all the points lie on one plane. So if all the corresponding points that I pick lie on one plane, this matrix A may have a rank which is smaller than degrees of freedom, this matrix A. Here rank 8 is correct because I have my corresponding points. Then rank A may be smaller than 8, so this was this matrix which was stacked from the corresponding points. And then I can't obtain a solution. Even if the points lie very close to a plane, this can get numerically unstable. So there's an example where you take the points here on the Sydney Harbour Bridge and where all those points lie very, very close to a plane, and then actually your computation screws up. You do not, with this algorithm, do not obtain the, your fundamental matrix. There's another situation where this can be problematic. So if the projection centers of your cameras are the same, so if I just take my camera, first image, and just rotate the camera and take a second image. So I don't shift the camera. Just take the camera, rotate the camera on the spot, and take a second image. If I do this, I have my first camera, which observes, let's say, those scene points. And I do the same thing for the second camera. I obtain the same points over here, but I can't, with a zero baseline, this is not going to work, because then if you look to the fundamental matrix, the matrix, the screw-symmetric matrix would be a zero matrix, which would eliminate all the elements of the fundamental matrix. So what I can't express, but this is an element of the fundamental matrix, is just the rotation of this computation. I always assume to need to have a shift, so non-zero baseline.
So the text of the second bullet would be this happens if the translation of the
This happens if the translation of the camera is zero between both images. Yes, if you only have rotation. So this O should be an I, not off if. Okay, so the next thing we can do now is, so these were kind of the two critical issues. And so actually, having no translation, only rotation is something which may happen. So if you have your camera, turn your camera on a spot without doing a motion, there's actually something which can happen in reality. And also the problem that the points shouldn't lie on a plane is something which can happen in reality, especially if you don't have an operator which selects the corresponding points, but if you have a feature detector which detects your corresponding points. Let's say you take pictures of a wall with a painting. Most of the feature detectors will actually generate features on the surface of the painting. If you take two images of the painting and you don't see further 3D structure, you run into problems over here. And you can test for that, because you can inspect the rank of your matrix A, but there's something you need to take into account that this can be a problem. Okay, the next thing we can have a look into is what happens if we have only 7 corresponding points. If we have only 7 corresponding points, the 8-point algorithm is not going to work, because we won't be able to solve the system of linear equations. But the fundamental matrix has only 7 degrees of freedom. So there should be the possibility to compute it using only 7 corresponding points. So the approach to do that is actually quite involved, or is more tricky to solve, and therefore I just want to sketch the idea how we can actually do that. So the idea is to look into the null space of F. So the vector space that is spanned by the vectors that generate the null space of A. So if I take into account the 2 vectors which generate the null space of A, and this must be now 2-dimensional. So one dimension is kind of, before we had from 8 corresponding points, we had our 1-dimensional null space and pick our fundamental matrix. If we have 7, it means that the fundamental matrix F that I generate, or the vec of F, which is F, must be in line with this equation. So it's a weighted sum of these 2 vectors describing the null space of A. So if I need to determine the 2-dimensional null space of A, these are these vectors F1 and F2, and this is one constraint that must hold. The next thing I know about my fundamental matrix, it has a determinant which is 0. So the determinant of my fundamental matrix must be 0. It's also something that I know. And if I combine these 2 constraints, so this constraint and this constraint, exploiting that F is a 3x3 matrix, this actually leads to an equation of degree 3, which I need to solve. And then I get up to 3 solutions, and these are 3 possible solutions for the fundamental matrix. So if I have only 7 corresponding points, I can come up with 3 solutions, up to 3 solutions for my fundamental matrix, exploiting the constraint. So I also build up my matrix A. I estimate the 2-dimensional null space of A, so I have this constraint, and I have the constraint that the determinant should be 0. And I can put both of the things together and then come up with an equation of degree 3, which I need to solve. This gives me up to 3 possible solutions for computing the fundamental matrix. So it's similar to the spatial resectioning, last lecture of photogrammetry 1, where we also have to solve an equation with a higher degree and then get multiple possible solutions out. So as a summary so far about this fundamental matrix, so everything so far was about the fundamental matrix except the mistake that I did on the slide. So what we looked into how we can estimate the fundamental matrix from corresponding points. We derived a simple algorithm which can do that for 8 or more points, just using the SVD. And we very, very briefly sketched an idea how this could be done with 7 points. So 7 is a minimal number of points that I need because I have this 7 degrees of freedom for my fundamental matrix. And so we can do that and obtain up to 3 solutions for that. So with this block, I'm now done with the fundamental matrix. And we'll make a 5-minute break. And then we move towards the essential matrix, do the estimation for the essential matrix, and then look also how we can estimate the essential matrix for special cases and how we can obtain the rotation and the baseline from this essential matrix. Thank you very much. Okay, so we can then continue and try to do the same thing for the essential matrix, and we actually can see that we can derive a very similar algorithm for the essential matrix, but the constraints that we have to impose are slightly different for the essential matrix compared to the fundamental matrix. So as a reminder again, the essential matrix can be seen as the fundamental matrix but for calibrated cameras. So the fundamental matrix was for uncalibrated cameras and the essential matrix now for calibrated cameras. So in the equation of the essential matrix, the 2 elements related to the calibration matrices are gone. And if we use the general parameterization of dependent images, we typically have this simplified form of the essential matrix, so it's only the product of the screw symmetric matrix encoding the baseline and the rotation matrix, which tells me how the second camera is rotated with respect to the first camera, and the first camera in this local frame is in the origin, and the rotation matrix is the identity, and therefore this expression here is simplified. So then also the coplanarity constraint can be formulated exactly in the same way, except that I have here already the corrected image coordinates. So if I have a calibrated camera, I have to apply the calibration matrix to the coordinates, I have the corrected coordinates, and then can use the essential matrix. So what we now want to do is we want to start with exactly the same idea as we did that for the fundamental matrix. And we can actually do a one-to-one correspondency to what we have done just a few minutes before. So we have the coplanarity constraint, and we do exactly the same what we have done for the fundamental matrix. We do that now for the essential matrix. So we have our system of linear equations over here. The only thing what we still have in here is our camera constant from the mapping into the camera coordinate system, the elements of the essential matrix. And then we can use exactly the same thing, build this system of linear equations with our point pairs, and have the kind of first algorithm for computing the essential matrix. Again, we built this matrix A to the Kronecker product of the corresponding points. We solve AF or AE, not AF, AE equals 0, and then build our matrix E based on the singular value that corresponds to the smallest singular, so from the singular vector which corresponds to the smallest singular value. And the question is now, which constraints do we need to impose now? Before, we said, okay, the third singular vector, the third singular value, sorry, should be 0, to impose this rank 2 constraint. And now we have an additional constraint that we need to take into account. So for the fundamental matrix, we said, okay, we decompose it so that D33 is 0, and we have our 2 original singular values in here. For the essential matrix, we can actually we can actually show, I don't want to go too much into the details here, that the singular values of the essential matrix need to be identical. So that D11 and D22 should be identical. And this is a result that can be obtained if what I basically do is, in here, I say I compute E transposed, and given the simplified form of the essential matrix, that it just consists of the rotation matrix and the screw-symmetric matrix, this simplifies to a form where this element eliminates the rotation matrix, and I only obtain my screw-symmetric matrix. So what I have is, so this was SB R transposed. So this is SB R transposed, which is SB R transposed R SB. So this eliminates, so it gets eliminated, or this transposed. And then I can exploit that SB tranposed equals to minus SB. This was an element of the screw-symmetric matrix. So minus SB, SB. And then I can continue that and can actually show that the two, so this is kind of the key idea, then I can exploit the property of the screw-symmetric matrix, which then shows that those singular values must be identical. As a result from this, the details you find actually in Wolfgang's script on that. Okay, so what I have done now up to here, I said, okay, those two elements must be identical, the two singular values. But I also know that E is a homogeneous matrix. That means I have a scaling factor, which I can multiply it, it will still be the same entity. So what I can do is I can simply move the scaling factor 1 divided by, so a D out of this system, so that those elements get 1. So this is identical to U, V transpose, nothing has changed except that I replace D by 1. And this holds because it's a homogeneous matrix, we have this scale parameter. So what I've done now, I kind of simplified this expression, or the constraint of the essential matrix. So for the fundamental matrix, I said I have to do this SVD and eliminate the third singular value. What I now do is I do the SVD and know that this matrix is actually a matrix which has 1, 1, 0 on its main diagonal. So this element over here. It's just imposing different constraints to the essential matrix. So the algorithm that I do again is exactly the same as I had before, except that this constraint, so the only difference sits down here where I had D11 and D22 before. So I build up my matrix A, I solve my linear system, A, E equals 0. Then I build this approximation of the essential matrix. I again compute the singular value decomposition of this approximation to obtain the U and the V matrix. And then I build up the essential matrix by having UA, this matrix which is 1, 1, 0 in its main diagonal, and the matrix V transposed. So I build up this matrix E, which takes into account the constraints of the essential matrix, but being the one which is similar to the approximation of the essential matrix. So this is kind of the only line that changes within the code compared to the fundamental matrix computation that we did before. So we can do exactly the same thing. The only thing is we exploit a different constraint down here to build up this essential matrix. But what still remains is the conditioning problem. That's exactly the copy-paste. The next slide was exactly the slide that I moved to the beginning. Therefore, there was this E and not this F. But exactly the same thing holds here. So we do exactly the same normalization. We compute the center of mass of the corresponding points. This gives me the center of the coordinate system. And I scale it so that all values lie between -1 and 1. Again, a few things about the essential matrix, about the properties. We knew already it's homogeneous. We had the determinant is 0. We had this additional constraint of the two singular values. and there's a third constraint which we are not exploiting here at the moment. This is a result of the properties of the screw symmetric matrix of real numbers that this expression holds. Again, if you want to dive very deeply into that, I recommend Wolfgang's book on that. We are not going to exploit that here in the course further. So what we did is we computed the essential matrix for the special cases, for the general cases. We now want to look into special cases of the essential matrix. So if I know something about the setup that I have, then I can actually simplify the computation in a way that I need less corresponding points. So the first thing we want to look into is if we know the rotations, we know how the camera has been rotated, but we don't know nothing about the baseline. Can we simplify the overall process? And this is the case, we will see in a second. So if we say, okay, this was a general form over here, which we can expand to the screw symmetric matrix and the rotation matrix. And now the rotation matrix is supposed to be known. So what I can do is I simply can convert the second image into a rotated image. So the pixel coordinates of this original point is simply in this this is index 1 over here, or the superscript 1 over here, which simply refers to the rotated image. I basically apply this rotation to one of the images. And then the only unknown that I have is this screw symmetric matrix that I need to compute. So the only degrees of freedom that I have now reduced from 5 to 2. Why 2? Because I know the baseline only up to a scale. I have 3 parameters, and I have this this scale that I typically fix the length to 1. This was one of the constraints in this general parameterization. So I have 2 degrees of freedom left. And the only thing I need to do is actually obtain this b, and then I'm actually done and know the baseline. So the question is now, how do we compute the baseline just given 2 corresponding points? Remember, don't need the length, only the direction of this vector. I assume to have 2 corresponding points, p and q, over here, so 1 pair and the second pair of corresponding points. And I can do a little bit of geometry and quite easily extract the baseline out. So again, this is a reference center of the first camera, reference center of the second camera, and we are interested in this baseline. So this is our unknown, this direction, the direction of this vector b over here. And I know that I have 2 corresponding points, p and q, which I can observe in both images. So this vector over here is the direction of p and the direction of q, and I have those direction vectors because I've calibrated cameras. So from the pixel, I don't directly know the direction where the point lies in space with respect to this origin. So I have 2 planes over here, and it's important that I have 2 planes in those corresponding points. P and Q do not lie in the same plane. But if they do not lie in the same plane, what I can do now, I can compute the normal vectors of these planes, these epipolar planes. How to obtain the normal vector for this plane over here refers to P. How can I compute that? So we're talking about this plane over here. How can I compute the normal vector of this plane? Okay, so what we have is, we have this plane over here. We know that these 3 points lie within one plane, P, O prime and O double prime. And what we want to do now is we want to compute the normal vector of this plane, the Norman vector. The question is, from what we know, how can we actually obtain the normal vector of this plane? Yes, exactly. So I have 2 vectors which lie in this plane. These are these 2 vectors. And I simply can compute the cross product of these 2 vectors. And then I get the vector which is orthogonal to that. So I get the vector which is orthogonal to the plane, which is our normal vector. And I can do exactly the same thing for the second plane. This plane over here, so I take this vector and this vector over here, so those 2 vectors, and compute the cross product, and then get the normal vector of these planes. So what I basically did is, I compute my normal vector on P and my normal vector on Q. And they are sitting, so one is sitting like this, and the other one is sitting like this over here. So now I have these normal vectors of these two planes, but these two planes are special. These two planes intersect in here, in B. This is exactly the thing that I want to compute. So the normal vectors of two planes which intersect. There's just one vector which is orthogonal to those two normal vectors. And this is exactly my vector B. So I have two planes. Let's illustrate this here. So this is my plane of my first plane over here, and this is my normal vector. And then I have my second plane over here, where this is my normal vector. So I have these two normal vectors over here. And the cross product of this normal vector is exactly this direction over here, and this is exactly the direction of this baseline. So by just computing the cross product of these two guys, I actually obtain this direction. Of course, I don't know anything about the lengths, but I don't know anything about the lengths of the baseline. Only direction matters, because it's anyway normalized to 1. So from obtaining these normals, I just compute the cross product of both. So the final expression is this one over here. And then I directly obtain my vector B, and I'm done. Of course, assuming I know the rotations, and this is the way how I can obtain the baseline, just knowing two corresponding points. But if you do that, the important thing is always what assumptions did we make or have we done in order to do these computations? Because it may be if I just pick two corresponding points and my computation fail. Maybe this can happen. There are a few situations where this can happen. So what are the assumptions that we made here implicitly when doing these computations?
Points P and Q do not lie in the same plane?
Exactly. So if P and Q lie in the same epipolar plane, this is not going to work out. Because the normal vectors would be the same, and then I would not be able to obtain this B over here. That's kind of the first thing. There are actually 4 assumptions that we have made implicitly. What are other assumptions that we have made? One of the assumptions was also similar to one of the assumptions we made in the fundamental matrix for computing the relative transformation, or relative orientation, sorry. If those 2 points are 1 point, just rotate my camera on the spot. It's not going to work out. So the length of this vector B must be larger than 0. So again, what I can't do is, if I simply don't move, I assume I know the rotations, but I don't move, this is not going to work out. So I need to have a movement in the camera, a shift from the locations where the images have been taken. Okay, what about these 2 things about those points over here? It is related to computing the cross product of these 2 vectors. When is this going to fail to provide me the normal vector?
Can you say it again, please?
So what happens? So for computing those normal vectors over here,
Yeah.
when can this be problematic? So what happens if you move these points P and Q further away? What happens?
If the angle at the point B becomes too narrow,
Yeah.
you get too narrow deformation.
Yeah, so if you have this point P and these 2 vectors, and the point P moves away from the camera, they become more and more and more parallel. And if the point is at infinity, we have these parallel lines. right? So the point shouldn't be too far away. If you take points on the horizon line for doing this, for doing the computations, this is not going to work out. And the third thing, which typically people don't think about, but which can be the case if you have, let's say, fisheye cameras, for example, if you have a point which lies on the baseline. So if this P or Q lies along the vector B, it's also not going to work out. So these are kind of our 4 key assumptions that we made in here. But the key take-home message is here, if I'm not in one of those degenerated cases, and from the practical point of view, important things are kind of the first 3, the last is often not that relevant. So you need to have a shift. The points must lie in different epipolar planes, and the points shouldn't be infinitively far away. Then 2 corresponding points are sufficient to estimate the shift of the 2 cameras if you know the rotations. So in special cases, you do not need a large number of points. You can do this with a much smaller number of points. And again, very, very briefly, if you have planar objects, so if all the points lie on a plane, if you know that the points lie on a plane, you want to exploit this, you can actually do that by computing homography which maps between those planes, estimate this homography. You can do this from 4 points. There's 4 corresponding points, you can estimate the plane. And then from this homography, you can extract the rotation matrix, translation matrix, normal vector, and distance from the origin. But again, this is a non-trivial solution, and it also works only for calibrated cameras. So it doesn't work for the fundamental matrix, only for the essential matrix. I don't want to dive into the details how this works. The important thing to note is if you have points on a plane, there's a trick to do that by basically computing the homography between those 2 planes, how they are seen in the first image and the second image. And from the knowledge that this is a plane, you can actually extract your camera parameters backwards. And last but not least, I want, again, just very, very, very briefly sketch the so-called 5-point algorithm. Because the 5-point algorithm is the gold standard that you are using if you want to compute. If you don't have to implement it on your own, if you have to implement it on your own, the 8-point algorithm is actually not too bad. But if you use a standard library and you want to compute the relative orientation of the essential matrix from corresponding point, Nister's 5-point algorithm is the standard solution to do that. So it's actually not very old, so proposed in 2000, or developed in 2003. It is an approach which only requires 5 corresponding points, or the minimal number of corresponding points, to estimate the essential matrix. It basically boils down to solving a polynomial of degree 10. Therefore, we have 10 possible solutions for this. And but the important thing why this approach is so successful, or has been so successful, is that if you use this in combination, if you have outliers or potentially outliers in your corresponding points. Let's say I give you 7 corresponding points, or 8 corresponding points, but it's a high likelihood that one of the points is an outlier. What one can do is one simply picks out randomly 5 of those points, computes the essential matrix, and then checks if this essential matrix is in line with the other pairs of corresponding points. So if the coplanarity constraint holds for the other points. And I can then randomize this process. Pick 5 points randomly, test it. Pick another 5 points randomly, test that. And then this is one way which allows me to identify inliers and outliers in my data sets. And the important thing of the 5-point algorithm is that it requires a small number of corresponding points, only 5 and not 8. Because the number of trials, I often need to repeat this process, scales very badly with the number of points that I need to compute this direct solution. So if I need 8 corresponding points instead of 5, I need much, much more trials in order to robustly identify inliers and outliers. And therefore, this approach is so successful because it's typically combined with a procedure, this randomization procedure, which is called RANSEQ. I was talking about, I'm not going to the details here about RANSEQ at the moment. But the smaller the number of points that I need to compute a solution, the easier it is for me to separate my set of corresponding points into inliers and outliers. And if I determine separated it into inliers and outliers, I take all the inliers and then compute the as accurate as possible solution for that. But in terms of the direct solutions, the 5-point algorithm is the absolute standard approach. Again, it's more involved, so in Wolfgang Förstner's script you find as an optional part the complete derivation of the 5-point algorithm. And they actually, this is the original publication for that, and there is also kind of a variant 5-point motion estimation made easy, which tries to simplify the description of this algorithm. But these are kind of the key resources if you want to look into the 5-point algorithm, how that works. But again, the important thing for me is that you know that there is an algorithm which requires 5 corresponding points, and why it is important to have algorithms which require a small or minimal number of corresponding points, because it can be so powerfully combined with techniques such as RANSAC, which helps me to separate my point set into inliers and outliers, which has a high practical relevance because the corresponding points are not free of errors. So if you take just feature extractors, you compare features and say, okay, they are similar, these are corresponding points. They can fail they can fail, or there's a certain probability that they made a mistake. You will have some outliers in there. And using RANSAC is a powerful tool to deal with that, and RANSAC is only efficient if you need a small number of corresponding points. Okay, what we learned so far in the last half an hour is how to obtain the essential matrix from corresponding points. For the simple algorithm, we use the same trick that we did for the fundamental matrix, but we now looked very briefly into 3 different variants. One was a 5-point algorithm, and then 2 with special cases. One if the points lie on a plane, again, just the idea sketched, or if you know the rotations, because then you can do that actually very easily. The final thing I want to look into is how I can actually compute the orientation parameters, so the rotation matrix and the baseline, given an essential matrix. So assuming I have the essential matrix computed, how do I obtain my rotation matrix R, and how do I obtain the direction of this vector B from these 9 elements I have in that matrix? So what we in short want to do, from E, estimate the screw symmetric matrix B, which means that I know B, and my rotation matrix. So the first thing is, question, is there a unique solution to that? So if I have an essential matrix, do I obtain R and S uniquely? Any ideas? So if I give you an essential matrix and you should compute R and SB, do you come up with a unique solution? Very good. Okay, let's start with what we want to have. So what we would like to have is first camera, second camera, we have our corresponding direction vectors to the corresponding points, and here those corresponding points intersect. So this is what we want to have. Consider that we're only looking here into direction vectors, and they have partially have homogeneous property for B, for example. I don't know what the lengths are, and this leads to potential problems. So the first thing I can do is, okay, this is set up, one possible solution to that. I don't know the lengths of B, right? So we to obtain B only up to a scale factor. What happens if I multiply B with -1? If I have a vector and I multiply this vector with -1, I basically flip its direction. So let's say I do that, I do that, multiply B by -1. B looks now in this direction, so that means O1 and O2 is swapped because B is always from O prime to O double prime. But it basically means I'm actually swapping those vectors over here, or it's from the geometry equivalent to that. So I actually would get those direction vectors. If I now compute the intersection of those 2 direction vectors, it would be somewhere sitting over here. The problem is my cameras look in this direction, but the intersection of the ray is behind the camera. This is a solution, a mathematical solution, but it doesn't correspond to physics, what the cameras can actually see. So this is one of the solutions I actually want to get rid of. This is what I want to have, and this is one of the things I want to get rid of. What else can we do? So we only look into direction vectors. If I rotate a direction vector by pi, so 180-degree rotation of a vector, it's still kind of the same thing, that this vector looks backwards. It means it's equivalent to the setup that one camera looks simply backwards in its backward direction. I'm just considering only rays over here. And so those rays, for the math, it doesn't matter if the cameras look in this direction or I flip this camera like this. We'll have the same ray over here. So if I kind of flip it around so that this vector looks downwards, I get this setup. So the lines will intersect somewhere very far away. Or I can actually do both, flip both of them, and then the point is somewhere down there. So the important thing is there are 4 solutions from math, but only one solution which is physically plausible, given that the cameras look into a certain direction, can only observe what's in front of the camera. So if I compute my solution, I'm likely to end up with having 4 solutions, and I need to take the one which is the only physically plausible one. This is kind of my goal now. Okay, so let's look into the math and see how we can actually obtain those parameters. So we said we have our essential matrix, and we know that the essential matrix can be brought into this form with a singular value decomposition. So I have my matrix U and my matrix V transposed, and I have this matrix which consists of 1, 1, 0 on the main diagonal. And those two guys, we are living in the space of real numbers. These are then rotation matrices. All are 3 by 3 matrices. These are rotation matrices in this case. Okay, so I have these rotation matrices, but there's something in the middle I can actually do. What I can do now is, okay, I'd simply define a matrix Z and a matrix W, which are of this form. So it's -1, 1, everything else is 0, the same over here, and additionally a 1 down there. If I multiply this matrix Z and the matrix W, I actually obtain this matrix down here, which is 1, 1, 0 on its main diagonal. So what I now will do, I will take this essential matrix, say, okay, this block over here can be written as ZW, which can be written in this form. So I take my essential matrix, say, okay, this can be written as a product of a matrix Z and a matrix W over here. Because the product of these two guys gives me exactly 1, 1, 0 on the main diagonal. What I can also do is I can now go in the middle and squeeze in an identity in here. Right? I can put an identity matrix in here, nothing changes. And the identity matrix can also be expressed as a product of 2 rotation matrices. The rotation matrix and the rotation matrix transposed is an identity matrix. So what I do in here is I squeeze in an identity in here, so I have the form U that U transposed and U W V transposed. Nothing bad has happened over here. The only thing on the design of Z here as a screw symmetric matrix, you can say, okay, I have my screw symmetric matrix over here, and this is actually a rotation matrix. So this is a rotation matrix, this is a screw symmetric matrix. That means, as I know my essential matrix is the product of this screw symmetric matrix and a rotation matrix, I can express this as this element being SB and this element being R. That's interesting. Just by doing some modification, just adding identities somewhere, I could split up the matrix in 2 forms, a screw symmetric matrix and rotation matrix. And the only thing I need to know in order to do this is I need to know U, I need to know V, and I told you how Z and W look like. And this U and this V I actually obtain from a singular value decomposition of E. Of course, this comes from the singular value decomposition. So if I compute the singular value decomposition, I take the U and the V, I define my Z and my W, I can actually compute SB and R transposed. The problem is, the only problem what I haven't told you, that there are multiple ways for defining those matrices. So this is not the only way how I can do that. And there are actually 4 ways for doing that. These basically consist of this matrix Z and this matrix W, the individual one transposed. But this is great because these are 4 solutions that we identified before, that there need to be at least 4 possible solutions from math, where 3 of them are not physically plausible and 1 is physically plausible. So the algorithm basically boils down to the fact that I compute the singular value decomposition and I simply try all 4 combinations and see which one is the physically plausible one. So the overall solution is okay. I have my E. By computing the singular value decomposition, I can actually say what SB looks like and what RT looks like. And depending if I use Z or Z transposed or W and W transposed, I get 2 possible solutions for the screw symmetric matrix and 2 possible solutions for the rotation matrices. So then I have 4 possible solutions for the essential matrix, and I basically check where's the object. Is it in front of the camera or behind the camera? If the corresponding point is in front of both cameras, that's the solution that I want, and I can discard the other 3. So basically, as a summary again, kind of the receipt is compute the SVD, compute the 4 solutions, test in which solution all corresponding points lie in front of my camera, and then return the only plausible and then unique configuration. So the important thing is, from the essential matrix, you can uniquely determine the rotation parameters and the baseline from the corresponding points by knowing where the camera looks to. So which point is in front of the camera, which point is behind of the camera. Which brings me actually to the end of the course today. So what we have done today is we looked into the computation of fundamental matrix and essential matrix and estimating the rotation parameters and the baseline given we have the essential matrix. We did that so far by requiring, or the algorithms we discussed are those which require a large number of points, which are these kind of 8 points, or at least 8 points, and larger than 7. And sketched some ideas how we can do that more efficiently, but really just a sketch, so nothing where I expect an in-depth knowledge. And these are setups where I can compute a direct solution, so it's not a process that I need to iterate and where I need to have an initial guess, an initial value for that. But what those algorithms don't take into account is actually the uncertainty, for example, of those corresponding points. If I have some corresponding points which I can determine very accurately and some which I cannot determine very accurately, this is something which is not taken into account. So from the statistical point of view, this is not an optimal solution, but it's already a pretty good initial guess. And this technique here is typically used, or those techniques here are typically used as an initial guess for then refining the solution with the least squares approach. And looking into these iterative solutions is something we are going to do in the next lecture. And the techniques we discussed here today are those which we need to init or initialize our iterative solvers for obtaining a statistically optimal solution. That's it from my side. Again, the key important references, the photogrammetry script of Wolfgang covers everything that I did here. Some things even in slightly more details, like how we continue here and show that the essential matrix has only two identical non-zero singular values, and the references to the one also kind of approach which says how good the 8-point algorithm actually is if you don't have outliers, and the 5-point algorithm from this stuff. That's it from my side. Is there any question that I can answer at that point? If it's not the case, happy to close a bit earlier and see you next week. Thank you very much.